I promise. Okay, let's go ahead and get started. We have a lot of exciting stuff to do today. We're starting what I think is one of the most fun parts of this course. So in particular, what we're going to be doing is developing a systematic perturbation theory, which will allow us to compute order by order in a perturbation expansion all of the various observables that we'll be interested in a quantum field theory. Okay. So just to set the basic stage, what we're going to start with is some sort of interacting quantum field theory. And of course, at the beginning, I'll just be considering a scalar field phi, which is what we've been focusing on. And our goal is to compute the natural observables of this system, which are the time-ordered vacuum expectation values of a bunch of insertions of that observable phi at various points in space-time. Okay. Now, just to remind you, we are interested in computing time-ordered correlation functions. And the reason that we're interested in time-ordered correlation functions is because of what we discussed last time, the LSZ formula, which tells us how to extract from the observables of the theory various scattering amplitudes. So, for example, if you have some final state and some initial state, then the scattering amplitude, that is which we call the S matrix element, the quantum amplitude for a collection of particles in some initial state to scatter at late times into some final state is basically given by a bunch of Fourier transforms of these time-ordered exponentials, of these time-ordered correlation functions of the scalar field expectation values. Okay, so for example, if you have a bunch of initial states, so here we have some initial states with momenta P1 up to Pn, and we have some final states with some momenta Q1 up to Q sub m, then what we do is we take the time-ordered correlation function, where we take n plus m insertions of this scalar field, and we take this time-ordered vacuum expectation value, and then we act on it with a bunch of these operators here. That's just the Klein-Gordon operator. It's the wave operator for a free scalar field theory, and then we take some Fourier transforms. Okay. So initially, however, I'm just going to go ahead and start developing some algorithm to compute these time-ordered expectation values, and then a little later on we'll discuss how that translates into an algorithm for the computation of these scattering amplitudes. Okay. And so far all we know how to do is compute this in free quantum field theory. And really all we know how to do in free quantum field theory is to compute the simplest two-point function, which is known as the Feynman propagator, or the Feynman two-point function. That's the time-ordered expectation value of phi x, phi y, and it's given by an integral d4k of I over k squared minus m squared, with an additional I epsilon there to remind us that when we do the K0 integral, we need to include the correct poles in this sum. And then we take a Fourier transform to give you the Feynman propagator in position space. Okay. And there are various different conventions for how this thing is normalized. Okay. So I've decided that I'm going to try and stick with the normalization conventions in your textbook, which puts a 1 over 2 pi to the 4th there. All this means is that there won't be other factors of 2 pi to whatever power floating around elsewhere. Okay. So this is a reasonably explicit and relatively simple expression for the Feynman propagator. In particular, in momentum space, this Feynman propagator is just 1 over k squared minus m squared. Okay. So it just is an analytic function of k that has poles at k squared equals to plus or minus m squared. K is plus or minus m. Okay. So what I'd now like to do is consider an interacting quantum field theory with a Lagrangian, that is to say a Lagrangian density, that's given by the Lagrangian of a free field theory. So this has some kinetic term involving the derivative of phi and the mass term, plus some interaction term that I'll just take to be some function of phi. Okay. And in particular, I'll just consider the simple case, which will be the easiest case for us to consider, where this interaction term is just phi cubed. Okay. So the phi squared terms are the kinetic terms that we sort of know how to deal with, and the simplest interaction term would be a term that looks like this, phi cubed, where g is some constant, which is known as the coupling constant of the theory. And this factor of 3 factorial is just a convention. Okay. And so the convention is that, in general, an interaction term say g phi cubed or lambda phi to the 4th, we'll just include a convention, so 1 over 3 factorial for a phi cubed interaction, a 1 over 4 factorial for a phi to the 4th interaction. That's just some convention because it'll make the results that we get at the end of the day a little simpler. Okay, it'll just make the results look a little nicer. Of course, we could always rescale g and lambda, these coupling constants, in order to get rid of those factors if we want. But for reasons that become clear, hopefully by the end of class today, you'll see why it's nice to include those factorials out front. Okay. Okay. So our goal then is twofold. So the first thing that I want to do is to compute these time-ordered expectation values exactly in free quantum field theory. Okay. So far in free quantum field theory, we've only computed the 2-point function. It's not actually going to be that hard to compute all arbitrary endpoint functions. So that means that we will have, in a sense, solved free quantum field theory in the sense that we've computed the expectation values of all of the observables in the theory. And what we want to do then, after that, is develop a systematic perturbation theory to compute these quantities order by order in the coupling constants in an interacting quantum field theory. So for example, if G is very small, if it's 1 over 137, then this systematic perturbation theory would give you very accurate results with very little effort. If, however, G is not very small, if G is a tenth, okay, or if it's 1 or 10, then this perturbation theory will not be terribly useful, and other methods would have to be used in order to study this quantum field theory. But fortunately, for many of the quantum field theories that we are interested in studying, one can reliably use these perturbative methods. Okay. And the way that I'd like to do, so as you've probably anticipated, the systematic perturbation theory that we'll be developing is Feynman perturbation theory, where we have a diagrammatic expansion that allows us to compute systematically all of the terms at a given order in perturbation theory. And Feynman diagrams are sufficiently interesting and important enough that I'm actually going to give 2 different derivations of the Feynman rules for interacting quantum field theories. Okay. So I know of at least 3 different derivations. I've decided I'll give 2 of them in this class. Okay. So in particular, there's one derivation that I'll describe this class, which is based on what's known as the Schwinger-Dyson equations. And basically, that algorithm, that strategy, involves writing down a set of recursion relations that relate these different correlation functions. And this will allow us, if you rearrange these recursion relations, to develop some sort of systematic perturbation theory, okay, basically by doing some very straightforward manipulations. Okay. There's 2 advantages of this approach. One advantage is that it's very clear in this approach that the only thing you're using about the field theory is you're using the commutation relations. All you use are the fundamental commutation relations of the field theory, and out pops some set of rules for computing and perturbation theory. Okay. A second, fancier way of deriving Feynman rules involves path integrals, or Feynman path integrals. That's a little bit more involved. Strictly speaking, we could get a very long way in this course, well into the second semester, without considering path integrals. But there are a lot of conceptual issues that I think are clearer when you think about things in terms of path integrals, and there are even some computations that I think are difficult, if not impossible, to do without thinking in terms of path integrals. So what I'm really going to try and do is develop first the Schwinger-Dyson equation approach and then the Feynman path integral approach. So the Schwinger-Dyson approach I really like because first of all it involves essentially no assumptions aside from the commutation relations, and it's very fast. I mean, we'll be computing Feynman diagrams by the end of this lecture today. Okay? So it's a very efficient way of understanding how to do perturbation theory. But in some ways, the path integral formulation is a little more intuitively clear, and it's a little more systematic. Okay, so I'll start by doing the quick and dirty way using the Schwinger-Dyson equations, and then we'll come back next week and give a more systematic development in terms of path integrals. Okay. So that's where we're going today. Before I get started, are there any questions? Okay. Okay, so if there are no questions, let's just go ahead and get started. Okay. Yes?
I have a question, actually. So it's about the LSZ formula. And it looks to me like, so you talk about there being initial states and distinct from final states.
Yes.
But it doesn't look to me as if there's really any meaningful distinction between the 2 of them.
Okay.
You could always just change you could always say, instead of having an initial particle with momentum p, we also have, we have instead
Okay, I'm drawing arrows to all of the things that are different. Okay. It's that time ordering symbol that is really the most important. Okay. So there's the plus to minus I, plus I versus minus I, which basically comes from the fact that you're considering a bra vector for final states and the ket vector for initial states. The really important thing is the time ordering. Okay. Yeah. Yeah, I mean, that's a good question. I mean, as you have noticed, okay, there are a lot of symmetries. Okay, so for example, you could imagine interchanging initial states and final states. And clearly, the LSZ formula tells you that in general there's going to be a relation between the scattering of particle A and B into particle C and D and the reverse process where C and D scatter into A and B. Okay. In fact, if you think about it, the fact that this S operator, so this has to be a unitary operator, so that immediately gives you some relationships between various different scattering amplitudes. Okay. The relationship between 2 to 2 scattering and the inverse process is a very simple version of that. But in fact, later on we'll discuss other relationships between different sorts of scattering processes that follow from sort of more complicated versions of this unitarity of the S matrix. So the optical theorem is the most famous example of this. It's relationships between various different scattering amplitudes. So yes, so indeed there is some similarity between initial and final states in this formalism. That's something that we'll be exploiting a little bit later in this course. Good. Yes?
I'm not sure I'm convinced about the fact that the only things that we know now the theories of these green functions.
Well, I didn't. So the question is, why are the Green's functions the only thing you need to know? Okay. It's not the only thing we need to know. Okay. So, yeah. I mean, you need to know all sorts of things. So I guess only, I don't know quite what you mean by the word only. You certainly need to know this Green's function. I would say that it's the only, I mean, I use the word only because it's the only time-ordered expectation value that we have as of yet computed in this course. Okay. It's the only one we know so far. In the next, hopefully in the next 45 minutes, you'll know a lot more. Okay. Good. Okay. Well, let's go ahead and get started. Okay. So the starting point from this derivation of the Feynman rules are the fundamental commutation relations between fields in quantum field theory. Okay. So let's say we have a scalar field at a position x and some time t. Then we know that its commutator with the scalar field at a different position but at the same time is equal to 0. That's just the analog of the statement that x and y, the operators x and y in quantum mechanics commute with one another. We also have an analog of the commutation relation between position and momenta, which says that the scalar field phi and the conjugate variable to the scalar field, namely the momentum density, which I called pi, which in the field theories we're considering is just d by dt of phi, they have a commutation relation which is a little less trivial. It's the commutation between phi and phi dot is a delta function that is non-zero when the two operators are located at the same point. Okay. And I've put in a factor of h bar here just to remind you that this is an intrinsically quantum mechanical effect. Okay. So later on, when we work out the rules of Feynman diagrams and the Schwinger-Dyson equation, it'll be useful to remember that every time we have a delta function here, you've got an h bar. Okay. That'll allow us to easily distinguish between which effects are classical and which effects are quantum mechanical. Okay. And so our goal is to compute a time-ordered expectation value. And more precisely, remember that in the LSZ formula, we weren't just interested in the time-ordered expectation values themselves, but rather the derivatives of the time-ordered expectation values. So here I'm taking the derivative with respect to the x variable of this time-ordered expectation value. Okay. So naively, what we'd like to do is use the equation of motion. Okay. So the equation of motion for this interacting quantum field theory says that the derivative, so that the Klein-Gordon operator acting on phi, well, in a free field theory, it would be 0. But we're working in an interacting field theory. So here's the Lagrangian. So we have that interaction term. And so the equation of motion will just set this equal to the derivative of this interaction term with respect to phi. Okay. In the example that we're considering, where we have a cubic interaction, this would be g over 2 times phi squared, because L interaction was g over 3 factorial times phi cubed. Okay. Now what's wrong? So naively what you'd like to do is you just like to take this differential operator and act it on that guy right there. The problem, however, is that that differential operator involves a time derivative, and we have this time-ordered symbol right here. Okay. So that makes life complicated, because that time-ordering symbol has a theta function of t, and when we take the t derivative of that theta function, we're going to get some delta functions appearing. Okay. So let's go ahead and sort all of that out. So the first thing that I want to do is ask what happens if I just took a single time derivative of this time-ordered product of the two fields. Oh, I guess I called them x and x prime. So what is this? Well, let me just write this out a little bit more explicitly. So the time-ordered product just tells us that if x happens later than x prime, we put this on the left. So we can write it as a sum of two terms. So a theta of t minus t prime says that t happens after t prime. So we put the phi of x on the left. And then we have to add the second term, which happens if x prime happens after x. So we get a theta of t prime minus t. Okay, so let's go ahead and take some derivatives. So the first thing that will happen is that the derivative will just act on this term here. Okay. And likewise, you can have the derivative acting on this term here. Okay. So if the derivative acts on those terms, then we can ignore the theta function, and all you get is the expectation value of the time-ordered product now of the derivative of phi with phi at x prime. Okay. So that's what happens if the d by dt doesn't see the delta, doesn't act on the theta function. There are also terms where the d by dt acts on the theta function. Okay. And what are they? Well, you get a delta of t minus t prime, which is the derivative of the theta function, of the sum of two terms. Well, one of them is phi x prime, and the other is minus, because there's a minus t there, phi x prime phi x. So that's otherwise known as the commutator of phi x with phi x prime, evaluated in the vacuum state. Now notice that we have this commutator multiplied by a delta function that sets t equals to t prime. So we can use the fact that at equal time these fields commute. So this is going to be 0. So we see that when taking a single derivative here, there's not too much subtle that goes on. You can just pass the derivative straight through this time ordering symbol. Okay. However, we're interested in taking two time derivatives in order to compute this operator up here. Okay. So let's do another time derivative. Now life is going to get more interesting. So, of course, so you can just see that we just need to really imagine redoing this calculation, except instead of that phi of x prime here, except instead of this phi of x here, we need to have the derivative of phi of x. Okay. So the exact same argument will go through, and we'll get just taking the time derivative of this equation up here, okay, namely this equation up here, we get the time-ordered expectation value of d by dt squared of phi of x prime plus the delta function coming from the derivatives of the theta function times the commutator of d by dt of phi of x with phi of x prime. Okay. All I've done is go through the same argument again, except instead of having a phi of x here, I had a d by dt of phi of x. And so we now get this second term here multiplied by the delta function that sets t equals to t prime. And so we now just need to remember a canonical commutation relation, which says that the commutator of phi dot with phi at equal times is a three-dimensional spatial delta function that sets x equals to x prime. Okay. So that means that this is the naive term, so two time derivatives, phi of x prime, plus a correction term, which is minus I h bar times the four-dimensional delta function that sets x equals to x prime. Okay. The time delta function was this guy right here, and the spatial delta function came from the canonical commutation relation here, along with that factor of I h bar. And a minus sign because I have the d by dt of phi before the phi instead of after in the commutator. Okay. So that means that if you're interested in computing, say, the derivative with respect to x squared, so this Klein-Gordon operator, acting on this time-ordered expectation value of two fields, then what you get to do is act that differential operator inside the time ordering at the price of introducing an extra delta function term. Okay. So and so we can then go ahead and use the equation of motion. So this is the equation of motion right here, to say that this is equal to the expectation value of the time ordered product of L prime at phi of x times phi at x prime plus a correction term that sets x equals to x prime. Okay. So let's just stare at this equation for a second. So let's consider the example of free quantum field theory. So in free quantum field theory, we had a name for this time-ordered expectation value of two fields. We called it the Feynman propagator. And in a free quantum field theory, the interaction term vanishes. And so this equation is just a statement that the Klein-Gordon operator applied to the Feynman propagator is minus I h bar times a delta function. Okay. That's an equation we've seen before. That's the equation that the Feynman propagator is the Green's function for the Klein-Gordon operator. So df is the Green's function for the Klein-Gordon operator. And you can see that we actually, so when we derived this originally, we computed the Feynman propagator by using the mode expansion, okay? And we worked it out in Fourier space, and then we just literally computed the Klein-Gordon operator acting on the Feynman propagator. But we now see that that was an intrinsic property that simply followed from the canonical commutation relations in quantum field theory. Okay? It was guaranteed to work. It was not an accident. Okay? So what I'd now like to do is generalize this formula up here, so write down a more general version involving n-point functions instead of two-point functions. But before I do so, let me pause here and ask if there are any questions. Everything clear so far? Everything unclear? Okay. Well, yeah, please interrupt. So this is sort of important, and what I'm going to write down now is going to be the basis for our first derivation of the Feynman rules. So if there's anything that's unclear, please do let me know. Good. Okay. So now what we'd like to do is ask what happens if you take this Klein-Gordon operator and act not on the 2-point function, but let's say an n+1 point function, where you have the operator phi of x that you want to take the derivative on, and a bunch of n other insertions of this field operator phi. So we know that there's clearly going to be one contribution to this, which is going to be the thing where the derivative operator just acts on this guy, forgetting about the time ordering symbol. So you'll get the time-ordered expectation value of the interaction term evaluated at phi of x times phi of x1 all the way up to phi of xn. Okay. But now we expect other correction terms. Okay. Just like we had this delta function correction term that arose in the 2-point function. So to understand what those correction terms look like, let's just first imagine the case where we have x2 up to xn all happening at very early time relative to x and x1. Okay. Then the argument that we use to derive this equation here would go exactly through as it did above. We wouldn't have to worry about the time ordering of x2 up to xn with these earlier time guys. So you would get a term that looks like minus IH bar times a delta function that sets x equals to x1 times the correlation function where you just got rid of x and x1 and you had all of the other operators that just would go along for the ride in this computation. So phi of x2 all the way up to phi of xn. So that's what would happen if you only considered the case where, say, x1 was close to x in terms of time ordering. So x1 happened at either before or after x, but all of the other operators happened much earlier. Now you could consider the case where, say, x1 and x3 up to xn all happened very early. Okay. Then you'll get a similar term, except with x2 eliminated from this series of terms here rather than xn. And if you think about it, you could repeat this argument for all of the terms that appear in this sum. So in fact, what you should get is a sum of delta functions times the time-ordered products, where all you do is you eliminate xj from this expectation value. Okay. Is it clear what's going on here? Okay. So first consider the case, say, where like n is equal to 1. Okay. Then there's only one term in this sum, and you just reproduce this equation that we've written right here. And all I've done here is generalize this to take into account the fact that if you have n terms in this time-ordered expectation value, you've got a bunch of different theta functions, and you've got to take all of those derivatives, and so you get a bunch of different delta functions, one at each possible time that x could be equal to. Okay. Right? Because you've got you have a d by dt derivative here, okay, and so you need to worry about all the theta functions with t is equal to t1, t2, t3, and so forth, which give you these delta functions down here. Okay. And just as in this two-point function, when you got this delta function, you had that commutator that removed the phi of x and phi of x prime and just set it to be a delta function. Here, you remove phi of j. So when you have a delta of x minus xj, you need to remove the phi of xj from this equation. So if this is not entirely clear, I encourage you, when you go home tonight, before you go to bed, work this out for the three-point function. Work it out for the case where n is equal to 2. Okay. And you'll see that this is exactly how it works. Okay. So this equation is quite famous, and it's known as the Schwinger-Dyson equation. Before Feynman came along, this is how people studied the perturbative computation of correlation functions in quantum field theory. Okay. This is the equation that Schwinger used in order to figure out the, I guess it was the anomalous magnetic moment of the electron. Okay. Before Feynman came along. What's that? They did. Schwinger and Feynman got a Nobel Prize for that. Good. And what is this? What this is it's a set of relationships between these various endpoint functions in a quantum field theory. And the important point is that it has terms that relate endpoint functions with different values of n. Okay. So for example, on this side we have an n.1 function, an n plus 1 point function. And down here, we have an n minus 1 point function. Okay. And up here, the number of insertions of phi depends on the interaction. But if you have a cubic interaction, then that's an n plus 2 point function. So we have a relationship between different endpoint functions in quantum field theory. Okay. And the other thing to notice is that this guy up here is an interaction term. So if the coupling constants are small, that thing's going to be very small. So when the couplings are small, what we have is a relationship between n plus 1 point functions and n minus 1 point functions. So what we're going to do now is reorganize this to develop a perturbative expansion for these correlation functions. And again, what I really want to emphasize is that so far everything that I've done follows only from the commutation relations. Any questions? So now, in order to make my life simpler and the equations that I'm going to write shorter, I'd like to introduce a little bit of notation. Okay. I get tired of writing zeros everywhere, and I get tired of writing t's everywhere. So when I take the time-ordered expectation value of something in the vacuum state, I'm just going to write it as an expectation value. And I'll never get anywhere in life if I keep writing these parentheses. So for now, instead of writing phi of xi, I'll just write phi sub I. And instead of writing phi of x, I'll write phi of x. Okay. And finally, instead of writing this Feynman propagator, d of xi minus xj, I'll just write this d of ij. Okay. And one of the things that you should note is that this is symmetric when you interchange I and j. Okay. The reason being that you have the time ordering symbol. Okay. You might think, so for example, let's say that xi happens after xj. Okay, then you might think that when you switch the two of them, you would get a minus sign. But you have the time ordering symbol, which just rearranges them back again. So this guy's going to be symmetric. Okay. And this is going to be the free propagator, or the free Feynman propagator. Okay. And finally, delta of, say, x minus xi, I'll write that as delta sub xi. So I'm just introducing this notation because otherwise I'll never be able to fit all of these formulas on one slide. Okay. Good. Okay, so let's get started. So now before we dive into interacting quantum field theory, what I'd like to do is completely solve free quantum field theory. That is to say, give you an algorithm, an easy algorithm for computing all expectation values in free quantum field theory. So consider free quantum field theory, okay? And for the time being, just to make all of the equations simpler, let me set m squared equals to 0, okay? At the end of the day, it'll be obvious how to generalize it when m squared is non-zero. This is just going to be so that I can write down fewer terms in my equations. Okay. And in deriving these Feynman rules, there's one essential trick that I'm going to use. It's a pretty dirty trick, okay, but it's a good one. Okay. So I'm going to use the fact that the free Feynman propagator is a Green's function. Okay, so all I've written there is the statement that when m squared is equal to 0, the second derivative of the Feynman propagator, that's the Klein-Gordon operator, when m squared is equal to 0, just gives you a delta function. Okay, so let's imagine then that I want to compute, say, the time-ordered expectation value of phi at x1 times phi at x2. Okay? So the trick that I'm going to use is to rewrite this in the stupidest possible way. I'm going to rewrite this as integral d4x of a delta function that sets x equals to x1 times the two-point function between phi of x and phi of x2. Okay. I haven't done anything here. I've just introduced a delta function for no reason. Okay. But the reason that I introduced this delta function is that I'm now going to use this delta function, this equation here, to relate the delta function to the Feynman propagator. Okay. So what is that? Well, that's then the integral, you get an I, so delta function, the delta function with x and x1 is I times dx squared dx1 phi x phi 2. Okay. Phi at x and phi at x2. Okay? Now I'm going to integrate that d by dx squared by parts. And I get the integral d4x dx1 times dx squared at phi x of the two-point function at phi of x and phi of x2. Everyone with me so far? Now I'm going to use the Schwinger-Dyson equation. What does the Schwinger-Dyson equation say? Well, I'm in a free quantum field theory. So let's just scroll up and remind ourselves of what the Schwinger-Dyson equation says. It says that when you act with this derivative, this Klein-Gordon operator here, you get an interaction term, which is 0, plus a delta function term. So in fact, I just need to use the simple version of the Schwinger-Dyson equation, which is the one that I wrote up here. Okay. So this interaction term here is going to be 0, and we see that d by dx squared of this expectation value of phi x with phi of x prime is just minus IH bar times the delta function that sets x equals to x prime. Okay. So you get a minus I from that Schwinger-Dyson equation, which cancels the I out front. Okay. And you get the delta function that sets x equals to x2. And like any sane person, I'm now back to using the units where h bar is equal to 1. Okay. So now let's go ahead and use the delta function to do the integral, and you get the Feynman propagator between x1 and x2. Okay, I haven't told you anything you didn't already know. That's how we defined the Feynman propagator. It was the two-point function, the time-ordered two-point function, between x1 and x2 in free quantum field theory. So nothing too impressive here. But I did this calculation really to show you this basic trick that I'm using, where I introduce a delta function by hand, and then I start integrating by parts, using the relationship between the delta function and the Feynman propagator. Yes?
Would you worry about boundary terms in this integration by part, or would you just say that fields fall off that?
Yeah, I mean, so this Feynman propagator falls off. Well, in a massive theory, it falls off exponentially at large distances. In a massless theory, it's a little more subtle. Okay, this is actually one of the problems that you're going to be doing for next week. Okay, not you, unless you want to. But yes, one could worry about that. But in a massive theory, for example, there's really nothing to worry about. Okay. One would have to work a little harder to prove that the boundary terms fall off, even in a massless theory, but it's fine. Okay. In particular, you'll show that in a massless theory, these guys fall off, the two-point functions fall off like 1 over the distance between the points squared. So this is like 1, so if you look at large x, this goes like a 1 over x squared, and this goes like a 1 over x squared. So you have a 1 over x fourth, and so integrating by parts is fine. Good question. Okay. Let's try something a little more interesting. So let's consider a 4-point function. Okay. So now I'd like to go ahead and use the same trick. So I get an integral d4x times a delta of x1 of the 4-point function between x with phi at x1, x2, x3, and x4. Okay. And I'll use the same trick I used above, where I write this delta function as I times the Klein-Gordon operator, or times the Feynman propagator, times the Klein-Gordon operator of the Feynman propagator, and then I'll integrate that guy by parts. Okay, so I get an integral d4x times the propagator between x and x1 of d by dx squared on this 4-point function, evaluated at points 2, 3, and 4. Okay. And now, as you can probably guess, I'm going to go ahead and use the Schwinger-Dyson equation to compute this derivative. Now I get some interesting terms. So what do you get? Well, I'm in a free theory, so there's no interaction term. So you get minus IH bar times the sum over all possible delta functions, where this phi at x happens at the same time as x2, x3, or x4. Okay. So there's that minus I, which cancels the I out front. And you get an integral d4x of dx1 times, well, let's just stare at this Schwinger-Dyson equation again. Okay. So you had to sum, so if you had 4 points here, say phi at x with phi of x2, x3, x4, you have a sum of 3 terms, one where x is equal to x2, another where x is equal to x3, and another where x is equal to x4. And then the delta function with x equals x2 is multiplied by the expectation value of phi of x3 and x4, and so on and so forth. Okay. So we just go ahead and plug that in, and you get a delta function, which sets x equals to x2, times this 2-point function between phi 3 and phi 4, plus the same term where x is equal to x3, times a phi 2, phi 4, plus a term where x is equal to x4, times a phi 2, phi 3. Okay. Sorry, it's having trouble making, there we go. So let's just go ahead and use those delta functions to do some integrals. So that first term will, the d of x1 times delta x1, we can do the x integral. What do we get? We get d of 1, 2, the propagator between points x1 and x2. And then we have that 2-point function of phi 3, phi 4, otherwise known as d3, 4. And then we get a second term, so the delta function gives you a d1, 3, and then you have a d2, 4, and a third term, which is a d1, 4 times a d2, 3. Okay. So what we see is that this 4-point function is now a sum of three different terms. They're all quadratic in this propagator. And basically what they tell you is that you need to sum over all possible pairings of these fields, phi 1, phi 2, phi 3, and phi 4 with one another. So there's a nice diagrammatic way of keeping track of expressions like this. Okay. So what I'm going to do is draw a diagram to represent this formula. And in this diagram, each point is going to denote one of these external locations, x1, x2, x3, and x4. And each of the lines is going to denote one of the propagators, d1, 2, d2, 3, d3, 4, and so forth. Okay. So for example, that first term I'll represent as a pair of vertical lines connecting the points x1 and x2 and x3 and x4. Now, oops, sorry, wrong one. Now I have to connect x1 and x3 and x2 and x4 in that second diagram. And then in the third term, I have to connect x1 and x4 and x2 and x3. Okay. So it's hard to draw a diagram like that where the lines cross on a two-dimensional page, so I'm trying to draw those lines hopping over one another. There's 1, 2, 3, 4 here, and there's 1, 2, 3, 4. Okay. So the rule is a point is an external location where the correlation function is evaluated. And every line is a free propagator, that is to say, a free 2-point function, d, that connects the points on either end of it. Okay. So these are Feynman diagrams. And these are the rules for computing Feynman diagrams in position space in a free quantum field theory. Okay. So intuitively, you should think of this as saying the following. We're in a free quantum field theory, so particles don't interact with one another. So if I have a particle here, it has no choice but to just travel along and become a particle somewhere else. Okay. So if you want to compute this expectation value, phi 1, phi 2, phi 3, phi 4, well, then it's a sum of three terms. There is one term which comes from the fact that the possibility that particle 1 turns into particle 2 and particle 3 turns into particle 4. There's another term which is that 1 could be 3 and 2 could go on to be 4. And a third term where 1 goes to 4 and 2 goes to 3. Okay. And it perhaps won't surprise you that one can easily generalize this in a free quantum field theory to compute endpoint functions for arbitrary n. So in particular, in a free quantum field theory, the correlation functions of an odd number of terms just vanish, and the correlation function of an even number of terms is the sum over all possible pairings. So let's say, I'll label those pairings. So let's say that one index I1 is paired with J1, all the way up to another index I sub n paired with J sub n. And then you get a bunch of free propagators that connect these various different points. Okay. So for example, in a 6-point function, you would have to consider all possible ways that these 6 different locations could be assembled together in pairs, and then for each one of them, you would write down a corresponding product of 3 free Green's functions. And so this result is known as Wick's theorem. And the process by which we replace, say, a phi 1, phi 2, and a bunch of other stuff, say, phi 3, phi 4, the process by which we replace this with a d12 times phi 3, phi 4 is known as a Wick contraction. So sometimes we state Wick's theorem as the statement that an endpoint function in a free quantum field theory is the sum over all possible contractions. And of course, by contractions, what I mean are contractions of pairs of fields to make Green's functions, or to make propagators. Okay. So I started out by considering the case where m squared was equal to 0. Now, hopefully you can understand how to generalize this to the case when m squared is not equals to 0, because the essential point was that I integrated by parts d by dx squared, acting on this guy, to make it act on this guy, and you integrated by parts twice, so there was no sign that went along, and so you could just add m squared to that formula there. I could, instead of having a d by dx squared, I could have a d by dx squared plus m squared, and you wouldn't get anything different. So this equation is going to be just as true in a theory where the mass squared is non-zero as it is in a theory where this is 0. Okay. So this is also true when the mass squared is non-zero. We just need to use the appropriate Feynman propagator for a free field with mass squared not equal to 0. Is everything clear so far? Okay. We're now going to get to the fun stuff, okay, where we start considering interactions. But before I get into that, I just want to check and make sure that we're all on the same page here. So now let's move on to an interacting quantum field theory. And in particular, what I'm going to do is use my cubic theory. So we have a cubic interaction, so that the extra terms that appear when we use the Schwinger-Dyson equation are quadratic in phi. And this will just be an example. In other theories, so for example the ones that I'll probably give you to work out on your next problem set, you'll develop the Feynman rules and the perturbation theory for other sorts of more interesting interactions. Okay. So let's go ahead and redo this calculation of the 2-point function in the interacting theory. So I want to go ahead and use this same trick. I introduce a delta function. That sets x equals to x1, and consider the 2-point function between x and x2. And now I write that delta function as I times the second derivative of the Feynman propagator. Now this is the free Feynman propagator still. And you get two derivatives. Well, you get the Klein-Gordon operator dx squared plus m squared acting on phi x, phi 2. Okay. And now I get to go ahead and use the Schwinger-Dyson equation. And what do you get? Well, you get now a sum of two terms. You get the term that we had before, which was minus I times the delta function that sets x equals to 2. Plus, you have an interaction term, which is the expectation value of phi x squared with phi 2. That's the new term coming from the interaction. So what we see is that this two-point function is equal to the same thing that it was in a free theory, namely d12, plus an additional term, okay, I seem to have missed a factor of I in my notes, but let's not get too scared and try and continue anyway. So we get an additional term that's proportional to the coupling times dx1 times this cubic operator. Sorry, this expectation value of something cubic in the fields. Now, in a free field theory, this cubic term would be just 0. Okay. So that means that this guy must be of order the coupling. It has to vanish when the coupling is taken to 0. So that means that this two-point function is actually going to be equal to its free value up to something that's quadratic in the coupling. Okay. So let's try and figure out what that is. Okay. So now what I'm going to do is I'm going to do a second sort of sneaky trick. Okay. What I'm going to do is instead of using that phi 2 here, I'm going to write phi 2 in, again, the stupidest possible way. I'll write it as an integral d4y of a delta function that sets y equals 2 times phi of y. And then I'll use the same goddamn trick to write this as I times the integral d4y times phi y times the second derivative with respect to y of this propagator, and then I'm going to integrate the y by parts. Okay. And so what you get is that this is equal to d12. Ah, good. That's where my I went. Okay. Sorry, there's a plus sign there, and so I get a minus g over 2, and I get an integral d4x, integral d4y of a d of x1, and a d of y2, and then I have d by dy of the x squared, or rather d by dy squared plus m squared of the expectation value of phi of x squared phi y. Okay. Now I go ahead and I use the Schwinger-Dyson equation again. So I get a d of 1, 2 times minus g over 2 times these integrals d4x, d4y, dx1, dy2, and I get the sum of two terms. So the first one just comes from replacing this, so acting this operator on this guy and using the Schwinger-Dyson equations to get the interaction term. So that gives me a g over 2 times phi x squared phi y squared. And then we have the various delta function terms. So those will be, you'll get a delta function which sets y is equal to x. And you'll get two of them because we have a phi x times a phi x times a phi y, and the phi y can contract with either of those phi x's. So you get a minus 2i times a delta of xy times the expectation value of phi x. Okay. So what we get now is, so you could keep doing this, okay, and keep developing a systematic perturbation theory. You add more and more terms in the calculation of this two-point function between phi 1 and phi 2. But what I'd like to do now is just work to order g squared so that we can get the leading terms in the corrections to this two-point function, phi 1, phi 2, in the case where the coupling is small. And so what we can do if we're working to order g squared is first let's consider this term. So this term is a 4-point function, and it has to be equal to its value in free field theory plus terms that are of order g. So if we're only working to order g squared, we don't care about those terms. Okay? And so what is this 4-point function in free field theory? Well, you have, this is what we just calculated. So it's a sum of 3 terms. So there's a dxx, dyy term, where you have the contraction between those 2 phi x's and those 2 phi y's. And then you have 2 different terms where an x is contracted with a y. Okay. So of those 3 different terms, 2 of them are the same. Basically, there's 2 different ways of contracting an x, the x's with the y's in this 4-point function. Okay. And then there'll be plus correction terms which vanish when the coupling is small, or is taken to 0. So if you're only working to order g squared, then you could just take this expression and plug it into here, and that would give you one contribution to this two-point function. The only thing left to do now is consider this 1-point function, the expectation value of phi x. So again, I'm going to compute this using the same sort of tricks that we've been using so far. So I rewrite this as a delta function that sets x equals to y times phi y. And then I write this as I times the integral d4y times the derivative or the Klein-Gordon operator acting on the Feynman propagator, which I can then integrate by parts and use the Schwinger-Dyson's equation to write as the integral d4y dxy. And what do you get? Well, the Schwinger-Dyson equation says that you get this interaction term, so a g over 2 times phi y squared, plus a delta function, but there's nothing to contract this phi y with, so you don't get anything there at all. And then, if I'm only interested in working to quadratic order in the coupling, I can use the fact, so let's write this as I g over 2 times the integral d4x, integral d4y of dxy times the expectation value of phi y, which is dyyy plus terms that have to vanish when you take g to 0. Because the 2-point function phi y has to be the free 2-point function plus subleading terms when you take g to 0. Okay. So let's go ahead and plug that in to this expression that we derived up here for this 2-point function. So we see that this 2-point function well, there was that leading term, which was just the free value. And then we have a sum of 3 different terms. Okay. So we have a minus g squared out front. The whole thing is going to be proportional to g squared. And what do we get? Well, let's first look at this term here. Okay. we have a dx1, dy2 out front, and then you get a dxx term and a dyyy term with a coefficient of 1/4 from that half and that half. And then you get a second term, which is 1/2 because of this factor of 2, dx1 dy2 times dxy squared. And then you have a third term, which is coming from this equation with this guy plugged in, which now again has a 1/2 because of this factor of 2 times, well, we had a delta function that set x equals to y. Yeah, sorry, there's no, yeah. So we have a delta function there. So you get a d of x1, d of x2, times a d of xy, d of yy. Okay. So we have this sum of three terms. Yeah, I mean, I was a little fast here. I used the same integration variable. Wait, I used the same integration variable y here as I did here. So I really should have been a little more careful. I should have called this a different integration variable z, and then used this delta function to do this y integral here, and then relabel that thing y. So that was a little fast there. In any case, I hope it's clear how to proceed. So what we end up with is an expression for this two-point function, which is the sum of three terms, all of which, oh, and I forgot, of course, an integral dy dx out front. So what we ended up with was this expression for this two-point function as a sum of three different terms. Okay. Is this clear? Did I do this a little too quickly? Okay. I'm sorry, it's a technical calculation. And at the end of the day, what we're going to write down is a set of rules which will free us from the burden of ever having to do these nitty-gritty calculations. But I think it's worth going through it all a couple times just to understand precisely how it works. Okay. Yeah. I'm sorry. I should have called this a different. I should have called that a z variable here, and then relabeled it at the end to be a y variable to get this term up here. Okay. Yes. There will not be any terms linear in the coupling constant. That's correct. Okay, good. Any other questions? I mean, that's a particular feature of this phi cubed interaction term that we've written down. Any other correction? Any other questions? Yeah, so just to reiterate, this last term, so we had this delta xy, which turned these guys into a dx1, dx2, which is this term right here. And then then this is just a dxy, dyyy. So that's these terms here. Okay. So let's go ahead and write this using our diagrammatic rules that we worked out when we were considering free field theory. So in particular, remember that the rule is that we had a point for each of our external insertions of the operator phi, a point for each place where this correlation function is going to be evaluated. And I would like to generalize this. So in general, a point can refer to any position, not just an external one. Okay. So it could either be x1 or it could just be one of these guys x in here that's integrated over. Okay. And likewise, a line is going to be a free propagator. And so the way that I want to represent this formula diagrammatically is, well, I have the leading result, which I'll write like this. And then what do these subleading results look like? Okay. So in that first expression, we have an x1 here, so that'll be a 1 and a 2. So we have an x1, which is connected by a propagator to an x. Then we have another propagator that just connects x to x. And then we have our point 2 here, connected to the point y, with another propagator that connects y to y. Sorry, that's not the most beautiful looking Feynman diagram. And then this next term, well, we have a propagator that connects 1 to x, and we have another propagator that connects 2 to y, and we have two propagators that connects x and y. And then the final term, we have a propagator that connects 1 to x, and another propagator that connects 2 to x, and then a propagator that connects x to y, and a propagator that connects y to itself. So these are the diagrams. These are the four diagrams that are associated with the four terms that I've written out here in my perturbative expansion for the two-point function. And the rule here, so the rules for computing these position space Feynman diagrams are that you start out with a point for each external insertion, or for each external location, xi, and then you start trying to connect them by lines. So, and then you start drawing lines coming off of each one of these external points. So in the present case, you had one line here, another line here. And the rule is that lines can connect with one another or they can split at a point where there is an interaction, which is usually called an interaction vertex. So in this phi cubed theory, you're allowed to have vertices where three lines come in together and meet like that. And the rule is that every time you have one of these interaction vertices, you get a factor of I times the coupling constant. Okay. This term has no powers of the coupling constant because the lines never split. And all of these other terms have two locations where the lines split in this trivalent vertex, this three-point vertex. So they each have two factors of the coupling constant. And this minus sign here, sorry, that's g squared, not g sub 2. That minus sign there is the I squared. And the next rule is that every time you have one of these, you get a propagator. Okay. The next rule that we use when we go between these Feynman diagrams and the actual formulas is that each internal, that is to say, not external position, is integrated over. And then there's one final rule to determine the numerical coefficient out front, okay, so there's this 1/4 here versus this 1/2, which, and this is the rule that sometimes gives people a little trouble, is that you divide by the symmetry factor associated with a given diagram. Okay. So in the present case, the symmetry factor of this diagram is 1/4, and the symmetry factors of these diagrams are 1/2. So we're running a little short on time here, so rather than try and cram it into the last -2 minutes that I have in class, we'll just defer the discussion of symmetry factors till next class. But the basic point here is that we now have a set of diagrammatic rules that allow us to calculate whatever we want. Okay. If you want to calculate a 2-point function, okay, you start by drawing down 2 points. Okay, it's a 2-point function. You draw 2 points. You draw 2 points, and then you start connecting them with lines. Okay, and you just draw every possible way that you can connect them with lines according to a set of rules. And in the present case, we have a phi cubed theory, which means the rule says that we're allowed to have a trivalent vertex. Okay. You should think of this, and you should think of this as a physical process. The trivalent vertex is a place where 1 particle comes in and 2 particles go out. Okay. 3 particles come in and meet at a point. It's a phi cubed theory, so it's natural for 3 particles to come and meet. In a phi fourth theory, you would have a quartic vertex where 4 particles could come and meet at a point. Okay. And so on and so forth. And one of the very interesting things about this procedure is that we see here that we end up with these closed loops. Okay. So in this case, we had 1 loop. Here we had 2 loops. And what do these loops correspond to? Each of these lines corresponds to a particle that's moving around somehow. And a loop corresponds to a particle that you never actually see in this external. You never measure. It's not a particle at one of the locations you're observing. Okay. These are what we call virtual particles. They're things that happen only inside the quantum mechanical process, describing the scattering amplitude. And what you can see is as you compute to higher and higher order in the perturbation theory, you're going to have a proliferation of these loops containing virtual particles. Okay. And this is why this perturbation theory is useful. Okay. Because at low orders in perturbation theory, these Feynman diagrams are relatively simple. The terms that we're going to be computing are relatively straightforward to study. But at higher and higher order, there's a proliferation of integrals dx that you have to do, propagators floating around, and so things technically get more complicated. Okay, okay, so we've gone through a lot this class. I recognize that this has been a lot of new material quickly. Don't worry, we'll be returning and studying more Feynman diagrams and Feynman rules next week. So before I end though, let me just see if there are any questions. Okay, I made my goal of deriving Feynman diagrams in 1 lecture, which is pretty cool. Okay, I'll see you guys all next week.